You may have noticed a connection between infinite limits and vertical asymptotes. For example, look at the limit as x approaches 1 of 1 over x minus 1 squared, and we see that that equals plus infinity, which means it does not exist, and the way in which it doesn't exist is that it approaches positive infinity. It gets bigger and bigger increases without bound. So we get a graph that looks like this, and indeed we see a vertical asymptote when x equals 1. And we see as we approach 1 from the left, it seems as if we're increasing without bound. As we approach 1 from the right, we're increasing without bound, and we have a vertical asymptote at 1. If we look at the limit of 1 over x plus 2 as x approaches negative 2, both from the left and from the right, from the left we see that it decreases without bound, and from the right we see it increases without bound. And once again, we do have a vertical asymptote at negative 2 this time, and we see as we come in from the left, decreasing without bound, as we come in from the right, increasing without bound, and there's a vertical asymptote. So there is a connection here, and let's look at the definition of a vertical asymptote, and that will make the connection explicit. Let f be a function and a real number. Then the line x equals a is a vertical asymptote of the graph of f if at least one of the following statements is true. The limit as x approaches a from the left of f of x is positive infinity. The limit as x approaches a from the right of f of x is positive infinity. Or the limit as x approaches a of f of x is positive infinity. And then we have similar things for the negative infinity. So any one of these 6 statements means that there's a vertical asymptote at x equals a. So let's find all the vertical asymptotes of the function 4x plus 4 over x cubed minus 4x squared minus 5x. Okay, so first thing we can do is try and factor this. And it does factor, and when we factor it, we notice that we have an x plus 1 term that cancels, and then we have x minus 5 and an x here. So that means that we have an x equals negative 1, an x equals 0, and an x equals 5 that are potential places for vertical asymptotes. Now, since this x plus 1 term cancels, x equals negative 1 here, that's the thing that would make the denominator 0, that thing is just a hole in the graph, because that factor ends up canceling. But these two do not cancel, so these are potential asymptotes. So how can we check to see if they're asymptotes? Well, one thing you could do is actually try and calculate limits as we approach them, either from the left or from the right. So I've chosen from the left here for each of them, and you can see that we do get values that indicate that there is an asymptote. And you could do this by plugging in a few values for x just to confirm what's happening. Or if you're able to, you can actually graph it. And so here's a graph of the function. We see that at negative 1, there is indeed a hole right here, but then we have 2 asymptotes, one at x equals 0, and then another one at x equals 5. And we can see that the limit as x approaches 0 from the left does indeed appear to be positive infinity. And I could have also checked it from the right. I would have gotten negative infinity. And then as we approach 5 from the left, we get negative infinity. As we approach 5 from the right, we get positive infinity. Either one of those indicate that there is a vertical asymptote at x equals 5.